Now we will discuss important properties and the theorems of the Z transforms, which are very important for us to utilize these Z transform techniques into the discrete time systems that we are going to discuss. Like in our S domain Laplace transform techniques, we have various properties and theorems and useful contributions by Laplace transforms to the continuous time systems. Similarly, we have various important properties and theorems of the Z transforms that are utilized in the discrete time systems. First thing that we will see in this important properties and theorems, you can say we are going for a multiplication by a constant. Multiplication by a constant A. For example, the constant is A. Now, let us say x of k is the signal or the sequence of numbers that we are having, and if it is multiplied by a constant, now what is the Z transform of a function a into x of k? We know that Z transform of x of k or x of kt is equal to sigma k is from 0 to infinity x of k z power minus k. Now with this into function where a is a constant, Z transform a into x of k, you can write it as sigma s k is equal to 0 to infinity a into x of k z power minus k. Now this entire thing is our function. Now a is multiplied with x of k, therefore that entire thing I have represented here, replaced it here. When you are having x of k, you are replacing x of k. When you are replacing a of k, when you are having a into x of k, you are replacing it here, a into x of k. Therefore, you can have this. Since a is a constant, a can always be taken out without loss of generality. Then a into sigma k is equal to 0 to infinity x of k z power minus k. Now, what is this function? This can be written as x of z. Right. Therefore, I can write this as a into x of z, because this braced bracket sigma k is 0 to infinity x of k z power minus k is nothing but equal to x of z. Therefore, Z transform of a into x of k, when you are multiplying any function x of k or x of kt or x of t with any constant a, then the Z transform of a into x of k is equal to a into x of z. Now this is multiplication by a constant. Now we will go with multiplying with a polynomial function. Multiplying with a polynomial function a power k. The second one, multiplication by a power k. As we have discussed in our previous class, a power k is a polynomial function. Now the function is, now what is our function? A power k x of k. Previously it was a power k, now it is a power k x of k. And what is the Z transform of a power k x of k? Z transform, by definition we can have it. We know that Z transform of x of k is equal to x of z, which is equal to sigma k is from 0 to infinity x of k z power minus k. Now with this in mind, sigma k is from 0 to infinity a power k x k z power minus k. Now this entire function is replaced here. Now if I just simplify this or rearrange this, I can have x of k a power k z power minus k. Now a power k z power minus k can be written as a inverse z whole power minus k. Okay, now can I represent this when you are having this in mind? you can just simplify this x of k a inverse z power minus k. Now by definition of Z transform, what is it? By definition of this Z transform, according to this equation, Z transform x of k is equal to sigma k 0 to infinity x of k z power minus k. Instead of this z, what are we having? We are having A inverse z. Therefore, when you are having z, you are calling it as x of z. When you are having A inverse z, we can call it as x of A inverse z. Therefore, you can have this as x of A inverse z. That is Z transform of A power k x of k is x of A inverse z. So that is how you are multiplying, pre-multiplying the z variable with A inverse, where z is the complex variable. Now we will go into the third property of Z transforms. The third property of Z transforms is linearity property. Linearity property. Let us say, for example, or for instance, the Z transform of, we have two different functions. Z transform of x of k is equal to x of z, and Z transform of y of k is equal to y of z, and when alpha and beta are constants, then Z transform of alpha x of k plus beta y of k is equal to alpha x of z plus beta y of z. Now with this in mind, you can simply utilize this function by this definition, the definition of Z transform. We get this one to be equal to sigma k is 0 to infinity alpha xk plus beta yk. This is the entire function z power minus k. Now if you separate these two parameters, these two factors, and multiply with z power minus k, and also use the summation sigma k is equal to 0 to infinity alpha x of k z power minus k plus sigma k is from 0 to infinity beta y of k z power minus k. Now since alpha and beta are constants, you can write alpha sigma k is 0 to infinity xk z power minus k plus beta sigma k is 0 to infinity yk z power minus k. Then by definition you know that this is x of z, and by definition you know that this is y of z. Therefore this can be written as alpha xz plus beta yz. So this is the linearity property. Any linear function, linear differential equation which is having x of k and whose z transform is x of z, and any function y of k whose z transform is y of z, where alpha and beta are constants, then z transform of alpha xk plus beta yk is equal to alpha xz plus beta yz, and the theorem or the proof goes like this, which we will be getting at alpha xz plus beta y of z. Now we will see the fourth point, which is the shifting theorem. Shifting theorem. Shifting theorem is nothing but you have two different types of shifting methodologies here. One is time delay and the other is time advance, the time delay and time advanced. Now what do you say, what do you mean by time delay? You have t, for example a unit step function del t. Unit step function exists for all time t greater than or equal to 0. Now when I am having this t and this is t for example and unit step function, then what is this function called? Del of t minus t, and this is time delay. Now when you have this same type of function which is minus t, and if it is like this, then this is del of t plus capital T for all t. Right, so this is time advance. Now such functions, how do you solve that using Z transforms? For a time delay function, how do you solve the time delay function? The time delayed or the time advance shifting theorem. So this is, here we are going to use a shifting theorem. We are going to use the shifting theorem, and here we are using real translational theorem. Right, we'll see what is this real translation theorem and complex translation theorem using the shifting theorem. Here, for example, we have two different Z transforms for this: x of t minus t, Z transform x of t minus t, and this other one Z transform of x of t plus nt and t minus nt, where n is the number of instants. Now for this you can say